Okay. Hello, everyone. Welcome to ICANX Talks, Connecting the World and Universe. My name is Lanfu, and I'm from the Australian National University. I'm going to moderate the talk tonight. And this week's the third week of August on bioengineering and energy. And tonight, it's great pleasure for us to have Professor Lianzhou Wang from the University of Queensland. Is going to give us the ICANX talks. And joining tonight at the panel also we have Huanping Zhou from Peking University. Professor Huanping Zhou and Professor Yi Du from Beihang University, as well as our ex-challenger. Our speaker tonight is Professor Lianzhou Wang from the University of Queensland. So I'm going to give a very brief introduction of Professor Wang. Professor Wang is the Australian Research Council Laureate Fellow in School of Chemical Engineering. He's also the Director of Nanomaterials Center and Senior Group Leader of Australian Institute for Bioengineering and Nanotechnology at the University of Queensland. Professor Wang's research focus is mainly on synthesis and application of semiconductor nanomaterials for using renewable energy conversion storage systems. And Professor Wang has contributed more than 500 journal publications, including top-ranking journals such as Science, Nature, Energy, and so on. He has also filed 18 patents and delivered over 100 plenary keynote invited presentations. In particular, in late 2018, his team has broken the certified efficiency world record of quantum dot solar cells, and so achieving 16.6%, so putting a little dot on that very famous NREL efficiency record chart. And Professor Wang is also serving as associate editor and editorial board member of more than 6 international journals, including Advanced Materials. His name's on the list of the Clarivate highly cited researchers. And also Professor Wang, of course, won many fellowships and awards. I'm not going to list to talk about to speak all of them. Basically, the highlights including ARC QE2 Fellowship of 2006, as well as this prestigious Australian Research Council Laureate Fellowship of 2019. And Professor Wang is also the elected fellow of Royal Society of Chemistry and Academia Europaea. So now, without further ado, let me welcome Professor Lianzhou Wang to the stage to deliver his ICANX talk. Professor Wang, please.
Thank you very much. Professor Lanfu, for the nice introduction. I just share my screen first. Can you see it?
Yes.
Okay, good. Okay, I'll just make this smaller. Okay, thank you very much. Thank you very much. Good evening, good morning, good afternoon. Anyway, so very nice to see you online. As said, my name is Lianzhou Wang. It's given me great pleasure to give this talk. And I would like to thank Professor Alice Zhang for organizing this wonderful platform. I just check the series. Today is over 110. Basically, I'm the 111 talk. So that means in the past 2 years, and Professor Zhang has been very busy in organizing the wonderful talks from all around the world, and also had actually a lot of recognition, and so a very good reputation in promoting the communication and promoting the collaboration around the world in the science world. So without further acknowledgement, I would like to go to my talk today. So today I'm going to give you a brief update on our recent work in the semiconductor nanomaterial development for the solar energy conversion. As I said, I come from the University of Queensland, Australia, and so basically the city is Brisbane. If you don't know this city, and if I say the 2032 Olympic Games will be in this city, and you will remember it. So welcome to visit us when when there's a chance. And talking about the solar energy conversion, actually we need maybe just don't need too many words. And basically, we are facing the challenge of fossil fuel, consumption, like the climate change, pollution, and really we need to push actually our technology and from the conventional fossil fuel consumption and to the renewable. And that's basically is our research interest. Our team has been focusing on the material development and for solar energy conversion, and go through two routes, basically two approaches. The first approach is from solar energy and through the chemical route, convert into the solar fuels, like photocatalytic process to produce hydrogen, and photoelectric chemical process doing the same thing, and all PV plus electrocatalyst to split water. And we also look at the other chemical reaction, like valuable chemical production, for example, CO2 conversion, and produce methanol and plus some other valuable chemicals. This is the solar to chemical approach. And the second approach is from solar to electricity generation. That's really about the new generation solar cell development. And we are interested in the low cost and high efficiency solar cell, and currently mainly about the perovskite-based solar cell. After we generate the solar electricity, this is basically green electricity, we also need to consider the storage. The storage is one of the important parts of the whole renewable energy sector. So in this area, and our team has been working with a number of companies, and so developing the cathode material and for the battery, like lithium ion, and also some flexible batteries. And considering the very broad audience of this webinar series, I will give some brief introduction of these three parts. Like for today's talk, it's mainly about actually the semiconductor nanomaterial development, and for the application in this solar energy conversion and storage sector. And I try to use three examples. And the first one is that semiconductor material design and for the photoelectric chemical water splitting and for hydrogen production. And the second example will be about the perovskite-based solar cell, and in particular, and we wish to address the stability issue. And the third example is try to combine the solar energy conversion and storage, and to design some integrated system, and that's basically focusing on the storage side as well. And so now come to the first example about the hydrogen production. The background information I don't need to go through, but if you look at in the past 3 or 4 years or so, and there are renewed interest, not only in the research sector, but also in the government industry sector about the green hydrogen. That's pushed by the climate change and also the fossil fuel crisis. And if you look at the different, the governments, like from China, US, Europe, and including Australia, Japan, and each country, basically, they put a lot of efforts in the research and the development sector to promote the hydrogen, production and the storage plus the utilization. So I don't need to go through all the details about the hydrogen's advantage. And basically, we have been interested in the hydrogen production sector because this also represents one for the very significant challenge. And if you compare with the current hydrogen production technology, like the natural gas reforming. This can produce hydrogen at very low price, $2 to $4 dollars per kilogram. So, and that's basically we call it green hydrogen. And now we really need to sort of moving away from this green hydrogen and to like to the green one. And so that's basically to the renewable one. And so in the midterm, and we looking at the technology like biomass conversion and electrolysis. That's electrolysis, can come from the driving force can come from the PV, for example, and or we can use some other type of gas reforming, but with the CO2 capture technology. But in the longer term, we also need to look at the large scale, low cost, more sustainable production process that's needed to borrow idea from our nature, our mother nature, that's actually come up with the mimic the nature's photosynthesis process, actually using the abundant renewable solar energy. That's basically some typical technology like PEC, photoelectric chemical cell, and all photothermal chemical process and the photobio related process. That's all related to how to mimic nature's photosynthesis process and to produce hydrogen. And so that's basically our focus has been on the photocatalytic process and to produce hydrogen. And I believe the audience, they all know this technology is not new. It has been there for half a century and 50 years exactly now. And one of the key components in the photocatalysis process basically is a semiconductor, and which can interact with the light. And so basically to have the charge separation upon the light in radiation. But in many cases, basically the charge like electron and holes can recombine very quickly, and that's basically release heat. That's what we don't want. We really want is to have the solar generated electron and holes can migrate and from the back and onto the surface to attain to enter the surface reaction. Like the holes have the oxidation power, and the electron has the reduction power, and they can do a number of important reactions, for example, water splitting. And if you look at this process, and we basically look at three key steps: the harvesting, light harvesting, and the charge separation and transfer, and certainly and surface reaction, and for the hydrogen and the oxygen production. And we need to focus on each step and to basically to improve the efficiency, and for the purpose of improve the overall solar to hydrogen conversion efficiency. But to date, after 50 years study, unfortunately, the solar to hydrogen conversion efficiency based on the powder form photocatalyst process has been very, very low. So the target solar to hydrogen conversion efficiency is at least 10%. Why 10%? That's because we need to compete with the gas reforming process from fossil fuel, and that's basically, and we need to reach that the efficiency, such efficiency to be able to sort of have the competitiveness. So in terms of the cost, compared with the traditional hydrogen production process. And if we look at the each step, and basically, and we need to improve, and so all this step. And but if you look at the key steps, just look at the time scale of the solar to hydrogen conversion process, and you can see it's cover a broad range of the scale. And for example, from light harvesting and to the surface reaction, and basically it covers such a big time scale. That means in some ways that certainly has some time limiting effect, and which actually will generate a lot of I mean the traffic, for example, the charge transfer can be seriously suppressed and cause the recombination. And if you look at I don't want to show the video today, and basically you may see many times when you read it with the light, and this solution will generate a lot of bubbles, and that means you generate split water to produce hydrogen. But if you remember, there's two half reaction, not only hydrogen produced, but also oxygen or other gases produced during this process as a mixture. That means this dangerous mixture also need to be separated. That's additional. That has additional cost. And for the powder form system, and so if you look at the state of the art technology, that's basically led by Professor Dorman in Tokyo University, and they can produce a very large scale, photocatalytic sheet, and but the efficiency so far is very less than 1%. So that's already the world best, and we still have a long way to go if we really want to achieve 10% efficiency. So when we also doing some powder-based photocatalyst, but we also consider the other options for hydrogen production, and certainly, if we really want to push the cost to be very low, and we go this direction, that's photocatalyst, but efficiency very low. If we really want to go high efficiency, and we're talking about like the photovoltaic driven electrocatalysis, that can also go high. And in recent years, the cost for the PV has been decreased quite significantly. That means actually this area has a lot of promise, but still, and really the cost is quite significant. And in between, actually there's another category called the PEC, as a photoelectric catalytic photoelectric chemical process. Actually, if you look at the photoelectric chemical process, that's a combined system. That's basically you have two half reaction, and for example, water oxidation and water reduction, and that's basically we want these two reactions happen on two electrodes. And in between, we have a wire to connect and to apply a small bias, and which can help and the charge transfer from one side to another. And this also will reduce the recombination. And in this case, the hydrogen and oxygen will be produced separately without any further separation process. That's what we have been working on in the past 7 or 8 years. And we come back to this simple equation again, and basically we are looking at the key parameters that can affect the absorption, charge separation, the transfer, and surface reaction. And in this case, we select a different material with different band gap, and we do the interfacial engineering, defects engineering, or facility engineering, and try to facilitate the charge transfer. That's basically to reduce the recombination and increase the separation and the transport efficiency. And we also to select a co-catalyst that try to facilitate the surface catalytic reaction speed. And so I will not introduce everyone, but today mainly focus on the second part of the charge separation and the transfer reporting, and to look at what's the strategy we are using and to improve the efficiency, and the overall certainly efficiency is the target and eventually. And so if you look at the electrode design, and so for the PEC system, that's basically we need two electrodes, and so one is the photoanode, another is photocathode, and this is not people from myself, it's from Professor Peter Yang's team, and a review paper. and they list basically the photoelectrode options. And so, for example, commonly use the photocathode in this blue color, and the photoanode in the red color. And if you look at the photocurrent, that's basically one of the key parameter, and so representing the PEC performance. And for most of the photocathode, they behave much better than the photocathode. But photoanode, like the silicon 3 and 5 group semiconductors, they are quite expensive. They are also not very stable in certain conditions. And if you look at the most studied photocatalysts like TiO2, they are all belong in the photoanode. That's basically for the oxygen involution process. This 4 electron erection is also the bottleneck of the whole PEC system. And what we really want is try to use our knowledge in the material design, semiconductor design, and try to actually improve the abundant metal oxide-based material. And in particular, as we said, this is the bottleneck on the photoanode side. And why we choosing metal oxide? Because they are cheap. They are, most of them actually quite low cost and also stable compared with the other semiconductor. And what we really want is to achieve a relatively high photocurrent. For example, if we really want to achieve this solid to hydrogen conversion efficiency of 10%, we really need to go through put this around this range. And so we started with the very simple one, with the most studied system like TiO2. TiO2 has been tens of thousands of people published in photocatalyst area, and we have been using this and try to get some understanding about the photoelectrode design. And we started from two-dimensional, and this actually Professor Gang Liu is now also in Institute of Metal Research, and that's go back to more than 10 years ago when he was a student visiting us, and we developed some nanosheet that's basically a very thin monolayer sheet like graphene, but it's but 1 nanometer in thickness. And we use this as a building block, like use layer by layer process to prepare the photoelectrode. And then we use this photoelectrode try to check the photocurrent. Unfortunately, and the photocurrent generated onto this photoelectrode is very, very poor. So those, of course, we found some other bi-reaction like the switch of current. That's maybe just a byproduct. But what we really want is to check to see how we can improve the photocurrent of this system. It's very so in the microampere per square centimeter range. So basically, we compare them, the theoretical photocurrent of the TiO2 is a milliampere. Basically, we have 100 times smaller. And one of the key problems we found is that because the nanosheet itself is very thin, and when we prepare the multi-layer thin film, basically the nanosheets covered layer by layer onto the substrate, and when the electron passing through, and the electron needs to go through from one layer to another, and that's basically the transport. The transport pathway is not that smooth. It's a lot of defects and trap size. And another thing is the very thin is may not absorb the light very significantly. Then we come up with the question for the TiO2 and how we can design that structure and to improve the efficiency. That means to unlock the full capacity of this material. And so then we come up with some other approach, still using TiO2 as the example, but we try to use a hydrothermal process to prepare the TiO2, and still this material has like layered structure, but it's not sort of a parallel packed onto the surface of the electrode, but it's vertically glued onto the electrode and on the F2 glass in this case. And we also did a number of characterization, and basically we understand there are a lot of porosity. That's because we use some protonated titanate as the precursor when we do some acid etching, we can generate a lot of porosity inside. This type of single crystal porous structure is very helpful for the charge separation and transfer, because the pathway of the charge carrier can be very short to reach the surface. And in this case, I don't need to go through the detail for that in the mechanism, but what we really want to see is the photocurrent generated onto this photoelectrode. We can see compared with the nanosheet we prepared before, and the photocurrent here generated is reach nearly 1 milliamp per square centimeter, is much higher. That's this gives us sort of some confidence when we change the nanostructure of the materials, and so that for the same TiO2 material, we can certainly increase the photocurrent density of the system very significantly, several times. And then we tried another method. This is a nanostructure, so like a nanometer side nanostructure modification. And then this another example. This can actually conducted by Dr. Yu Xiang, who is now in Beijing University of Technology and Engineering. And Yu Xiang basically was working on the lithium-ion battery. Zhejiang was working on photocatalyst. And these two young fellows, they discussed, and they merged, they combined the idea of the lithium insertion, lithium ion intercalation mechanism with the photocatalyst. And the idea was to provide some built-in electric field into the system. And in this case, if you look at the common photoelectrode, basically, particularly in the bark, and so the bending is only on the interface between the bark face and the electrolyte. That means actually the charge carrier driving force and for the electron and holes is not that significant. But in this case, so these two young fellows' idea was to insert the lithium into the ion, the TiO2 nanostructures. And why doing this? Because if you look at the TiO2, titanium and oxygen, that's form a very beautiful octahedral structure. But if you insert some species in between, and basically you would have led to the distortion of this this symmetric structure, and because of the asymmetric structure formed, that's not symmetric anymore, and there will be some dipole formed during this process. This the dipole and will lead to the built-in electric field in the whole film system. This system is will led to the band bending, actually provided the driving force and for the charge separation to happen more efficiently. That's the idea. And we started with the lithium insertion process and using the titanium as a electrode for the lithium-ion battery configuration. And if we doing the insertion, we will see basically when we insert the lithium into the species, we can see actually that the peak of 200 is become means the lattice 200 become larger, is to shift to the smaller angle, and then another 004 peak angle becomes smaller. That means that the octahedral structure has been squeezed, and that's generates distortion. And we also applied the surface potential difference and to understand the structure change. Basically, after we insert the lithium species into the structure, we generate the surface will have more surface photocharged hole accumulated. That means, and so we also look at the built-in electric field, and after insertion, we will see there's certainly some electric field generated in this 7 micrometer thick film, and with this, and we look at the photocurrent generated onto the system, and after the insertion, we will see, and the photocurrent generation is several times larger than the TR2 without any insertion. We also look at how this method can be generically applied to other systems, like we insert sodium and other species. They also have some phenomena, some effect, not that significant as lithium, but certainly they also has an effect. And so these two examples basically give us the confidence for one material, TiO2, if we can understand the structure and modify the structure from the atomic scale, from the nanoscale, and we can certainly improve the PEC performance and to reach the possible maximum of the photocurrent. And then, but as I said, TiO2 is a very low and very wide bandgap material, and it still cannot reach very high solar to hydrogen conversion efficiency. Then we shift and we move our interest to the narrow bandgap photoelectrode, like Bismuth Vantage. This is sometimes Wang's work, and he applied a very simple method, electrochemical treatment, actually onto the bismuth vantage produced also by hydrothermal process and to the system. And this basically applied a very small negative bias for about 2.5 minutes, and they will, you see, they will the material have a very significant increase in the photocurrent generated onto the system. And so, and we try to understand why, and why a small bias and the negative bias to the photoelectrode can generate such a big photocurrent improvement. And basically, this may related to the partial reduction of the species, like bismuth 3+ and vanadium 5+, it can be reduced to 2+ and 4+ respectively, and in this case generates some oxygen vacancy. The oxygen vacancy and can be formed, can behave like some zero donor level, and actually to promote, to improve the charge separation and the transfer property, and leading to quite significantly improve the photocurrent in the system. And from this example, we sort of realized the importance of oxygen vacancy and in the PEC system. And so then we try to further continue to understand this system. And if you look at this this one word, photoelectrochemical, and basically we can split it into two, cut from in the middle, and one is the photovoltaic effect. The other one is the surface chemical, electrochemical reaction. And so, and this was conducted by Lianzhou Wang, and he chose another narrow bandgap for semiconductor iron oxide as the photoanode, and basically we intentionally to introduce the oxygen vacancy in the film, and by controlling the atmosphere when we do the calcination. And in this case, and the traditional understanding is that, and if you have increased the oxygen vacancy, it will have increased the bulk transfer, transportation, and it's in some way it's correct. And if we look at the film we prepared in air and in nitrogen for different time, we will see the photocurrent all increased after we introduced the oxygen vacancy in nitrogen, but it's not linear increase. And basically, if you look at the carry concentration and the increase, for example, towards this direction, but it's not linear increase. and to contribute to this photocurrent, basically reach a certain level and then they form a volcano shape. That means the charge carrier and in the system and play a quite significant role. So in affecting the photocurrent. And then we try to decouple this and into PV and the EC system. And so the first, let's look at the surface electrochemical reaction, and we did some experiment and also the calculation simulation work. We found basically after we induce the oxygen vacancy and the surface oxidation reaction, the oxygen evolution process can be accelerated. That means oxygen vacancy is good for the surface reaction. But if you look at the PV effect, that means in between the bulk and the interface and between the solid and the electrolyte, and it's much more complex. And if you only look at the photocurrent, so like a PV effect, and after we introduce the oxygen vacancy, certainly the photocurrent can be improved. But if you look at the VOC, and this one has become smaller, and we also look at the charge separation process and the charge recombination rate, and also the flat band shifting behavior, and basically we found so the role of oxygen vacancy in this whole system and can be divided into three key parts. So in the bulk, that means in the film, and on the interface and on the surface. For the surface, this is the electrocatalysis process, and so basically it's, the oxygen vacancy is good for oxygen evolution, and in the bulk, and it can also help the charge transfer behavior. But on the surface, because of the introduction of oxygen vacancy, and this one basically will behavior like the trap state has the pinning effect, and to prevent the split of the Fermi level between the electron closed Fermi level and the whole Fermi level. And in this case, basically you have a very relatively low VOC. And in this scenario, basically the bulk transfer can be accelerated on the surface, accelerated, and so in the middle and on the interface is not good. The oxygen vacancy is not good for the whole system. We really need to actually optimize the whole system and to look at the overall photocurrent and to see how it can improve the efficiency. And based on our understanding about the oxygen vacancy, we also look at the other system like the disadvantaged system and also the photocathode system. I don't have time to introduce today, but you can look at our recent paper if you're interested. And as I said, the overall, the final target is still try to reach the efficiency that's actually as high as possible. And for the solar to hydrogen conversion efficiency, we still choose this magnet because it's relatively stable and high performing. And we wanted to actually combine using some semi-transparent magnet as the photoelectrode and to achieve as high as possible photocurrent. And so in this case, and by combining this the photoelectrode with a solar cell, and we prepare so-called artificial leaf. And the working mechanism is something like you have light irradiated under the photoelectrode and generated photocurrent with this red curve. And then because of the semi-transparency and part of the light will passing through and to activate the back side perovskite solar cell, and in this case generate another photocurrent. And so this RV curve, and this crossing point is the working point for the solar hydrogen conversion without any external bias, and we can produce the hydrogen at a relatively high efficiency, but 6.5, and certainly there's still a lot of room to further improve. And so if you look at the future and what we can do, I think this is my understanding. I think for perovskite solar cell, and it's have very high photo current. So that's not a problem at all. And the key limit effect is still to have a very high performance for the photoelectrode. For example, if we can further improve this radical and to improve up to around, to push around up to here, and we should be able to reach even high solid to hydrogen conversion efficiency. But certainly there's a lot of efforts to further improve this. And so then in this regard, we also try to use we understand the importance of material. We also try to use some machine learning approach to design the semiconductor. For example, this is another example. This recent example, we try to apply the machine learning to help us design the material. But there certainly, and there are many more things, and so we can try. And so if you look at the material selection, and we also look at another promising material, and the star in the perovskite solar cell. So this basically this type of hybrid perovskite. And why we consider this? Because this material, I think, has all the merit, all the advantage for to be used as a good photoelectrode material for the solar hydrogen conversion. But I think the problem is the stability. So certainly it's a lot of promise, and that's really depends on how our talented people, like in the audience, maybe you can find some good way and to further improve the efficiency and to reach as high as possible solar to hydrogen conversion efficiency. So then now come to the second talk and related to the perovskite, and we try to address the stability issue of the in the perovskite solar cell. And so I think the first one I maybe talk too much, but I so need to be quick. So the next generation solar cell has been driven by mainly two things. The first one is the efficiency, and the second one is cost. Certainly the stability, toxicity as another key important things that need to consider. And in recent years, if I think the silicon solar cell has witnessed a great success, but still actually the cost and the environment impact of the system is still relatively high. And if you can consider all this process, and in strong contrast, actually, and the solution process, the solar cell, like the perovskite, and it's generates a lot of interest from research and industry. And I don't need to go through all the details about the background. And so basically the perovskite, they are a large group, and they contain some organic and metal halide perovskite. And so that means A side, and it can be some organic species, and there's a plus lead and the iodine. So halide-based species, and to form a typical perovskite structure. And the first example certainly actually is produced by this Professor Miyasaka about 15 years ago, and at a very low efficiency. But in the past 10 years or so, we have seen such big success. It's now 25.7%. And actually, one of our panelists, Professor Huanping Zhou, had done great job in this area. And the process of this process certainly is a very chemical process compared with the silicon-based one. It's very cheap, and also it's the working process like perovskite absorb light, and then on the other side, actually on two sides, one side has the electron transport layer, on the other is a Hall transporting layer, and there's because the perovskite have very good charge diffusion process. Actually, it can have very good charge separation. And if you look at the Venn diagram, and this will lead to very high efficiency and in the perovskite. And the working mechanism is relatively simple. But if you look at the research challenge, I don't think efficiency is a challenge anymore. It's very high efficient already. But if you look at the stability, and certainly this is very, very significant. So if you don't, you cannot compete with the silicon with 25 years, lifetime on the rooftop. It's very hard to have a large scale production. And so we need to significantly improve the stability of the material. Why it's not stable? And intrinsically, and then so basically this material, if you look at the A, B, X side, and the bonding between these species is very weak, they can have a lot of defects, and they can have a lot of ion migration, which will actually degrade the material relatively quickly. And if you look at the external stimulus, like moisture, light, oxygen, heat, everything can damage the material and it actually decompose the material and to let the solar cell to lose the function quickly. And what we have been working on in the past few years is to try actually to address the stability issue, because we think this is the most important thing actually for the commercialization of the system. And we try to use a few approaches, and for example, and to address the heat, moisture, light, and also the intrinsic ion migration within relatively large grain size of the perovskite. And so, for example, the first example is to try to introduce a two-dimensional perovskite. And so this Peng's work, I think we are one of the very first example to introduce the two-dimensional material on the top of three-dimensional perovskite, because the two-dimensional perovskite and it can be much more hydrophobic and also much more stable. But the problem is less conductive. And so Peng applied a very thin layer of two-dimensional material on the top of 3D to protect the material. And so we found actually other functions all relatively similar, but actually the VOC and has quite a good improvement. And we try to understand why we apply such a small capping layer on the top. And so it can help increase the VOC. And in this case, we like to use the contact personal difference measurement, and we see basically apply the two-dimensional material. It will actually help to improve the split of the Fermi level between the hole and the electron core Fermi level, and which actually will facilitate the charge the whole extraction and in the device. And we are more interested in the stability. And in this case, basically, if you look at the stability test, and with and without the two-dimensional capping layer at a high relative humidity, and so after 1,000 hours, certainly actually the capping layers one is much better. We also look at the different temperature, and which all have showed relatively promising results. And so, and then another example is try to use some other low-cost capping layer. Like in this case, actually, is to introduce, for example, a carbon. So we use a very simple surface modification process to introduce a silane, for example, in this case. And then after we introduce the silane and introduce the carbon-60 as the electron transport layer. So and after this, and we deposited the perovskite, and on the top we use another carbon electrode, and so to cover this, and this basically form like wrapped carbon carbon layer on the on the surface, because on the top and bottom all wrapped with carbon, and so because carbon tint process actually to cover this perovskite, because carbon is also quite hydrophobic and it will prevent the moisture attacked. So in this case, we can also reach relatively high stability, and so at a relatively low cost. Of course, the overall efficiency PCE is not very high. It's less than 20%, but stability is pretty good and also is pretty cheap. And another example is try to mitigate the damage from the UV light. And so if you're working on solar cell, you will know basically solar cell and electron transport layer normally is a compact layer of TiO2. TiO2 itself is a photoactive material. And if you irradiate with sunlight, there will be certainly be UV light. And this UV light can actually have a high energy, which can damage the perovskite. And so because of the photoactive function of the TiO2. And in this case, and we try to introduce the concept of down converting process. That's basically we use a dopant, European doped TiO2. And so in this case, the function of this dopant is to absorb the UV light and which can convert into the visible light. That means less damaging material. And if you look at the process after doping the down converting material, and the device has improved photocurrent, and so that's JFC. And so we also look at the stability and the UV light for 500 hours, and certainly the stability is much better. And then to tackle the intrinsic ion migration within the bark film, and we try to going down. That means we try to decrease the particle size to as small as possible, and that means goes to the perovskite quantum dots. And in the quantum dots, basically, for each dot, it will be surrounded by some surface ligand. This ligand will protect the dot, and but the ligand also has a problem of insulating and block the charge transfer. How to reach a balance, and that's a tricky thing. And so then we developed a new method. That's because the ligand assistant A-side cation exchange approach. And we basically using this approach, and by intentionally control the concentration of a surface ligand, and we can produce a mixed cation quantum dots at a very high, very short time window, and actually which also have very good quality, and in terms like the PLQR. And so we can also tune the composition of the material and tune from PLCesium based or to PLFA based one. And from one to another, you will see the band gap change and the color change. Also, the size can also be tuned, and so optical properties are certainly different. So, and by using this, and so like this one from our panelists, and so Professor Yidu, and they help us to take some beautiful image, and it also has highlight as the front cover of the journal. And we use this building block and the quantum dots and to prepare the solar cell, and which actually have so very tiny particle. If you look at this compared with the bark film, and the grain size is much larger. And this small size, the one that means it's surrounded by the surface ligand, which will protect the material and from the migration to happen quickly. So, and fortunately, a few years ago, we got a very good efficiency, and so they certified also recognizing this NREL's chart, and we more interested, and I think we are more interested in the stability of the material. And our hypothesis or our expectation is that by tuning the particle to small size, and we should be able to keep the material phase stable, and that's what we expected. And our measurement also proved that that's true. So basically, because of the activation energy after we getting smaller size and can become larger, that means much more stable. And if we irradiate the device continuously for 600 hours, and that quantum dots device still have 94% of original PCE, but the other ones actually lost relatively high percentage. So for the bulk one, so and we try to scale up and try to prepare the quantum dots onto larger size, a larger type of substrate, go to flexible, and this is all the work we have been doing currently. And we also try to use another method to tackle the perovskite stability problem. For example, here, and we try to combine the perovskite with another morph, that's a metal organic framework. This on top of a porous material, and we try to use a very scalable process like this Dr. Jing Wei's work, and to use a ball milling process, and to put the ZIF glass and the perovskite together into the ball mill system, and then we heat this composite. During the heating process, basically this morph will be melting. The melting process will wrap on the surface of perovskite to protect the perovskite and from attacking by attacked by the moisture, by the water, and in this case, and so we can realize a very high stability in this composite. For example, we put the composite into water for up to 10,000 hours, and we still keep over 80% of the PL emission, and we also can tune the composition and the size and the shape, or the color, the light emitting color here, and which can be stable for a very long time. And this material also have some level for photocatalytic process, but actually we certainly need more efforts to further improve the photocatalytic performance in this regard. So then the last example, I think maybe 5 minutes for my talk, will be the integration between the energy conversion and storage. And so the idea was to use the solar cell to generate electricity, but we also want to simultaneously store this energy and into the battery. And the design of this one is based actually on Dr. Yuxiang's work, and we designed a type of aluminum-ion battery, and first, and then we try to combine the aluminum-ion battery and with the solar cell. And in this design, aluminum-ion battery has a piece of aluminum sheet as the anode, and then this aluminum sheet will be also shared as the current collector for the solar cell. That's basically in one piece of it, and we have aluminum-ion battery and plus the solar cell. The solar cell, because for one solar cell can only provide the VOC about 1.1 volt, and to charge the aluminum-ion battery, we need around 2.5 volt, and basically we need to use 3 solar cell and linked in parallel, so in series, and to provide about 3 volt open circuit voltage, and to drive this, to charge this aluminum-ion battery. And when we irradiate it with light, and the solar cell start to work and to generate electricity, which will be charging this aluminum-ion battery. And when we remove the light, and it's actually the stored energy can be discharged from this aluminum-ion battery. And this is the basic idea. And as you can see, this is a very small piece of device, and it can also be flexible. And so basically, we look at the overall conversion efficiency. That's basically from solar energy and convert into the solar cell, and generate around 18% efficiency. And then from solar cell charge the battery, and finally, and we can have usable energy from the aluminum-ion battery, still over 10%. This is relatively high value, and so at this stage. And why we're doing this? Because we are working with some company, and which asks us to do the printed battery. The printed battery will be used to power some functional device like wearable electronics and implantable, and that's use the roll-to-roll, large-scale production. And this just to give you some example we are working on, and basically this is a small trial, and we printed a battery and powered with RFID as the name tag. And this is on our UQ campus. We have our students and the staff run for 10 kilometers on the campus, and just using one laptop to monitor each runner's position, because actually it's have the so responding system, and so it's went well, and so now the company is doing the large scale production with this this device. And with this, I think I run out of my time. And if you have any further interest, you can see the recent review paper from our team. And with this, I would actually like to do a brief summary. And so the first example is the solar conversion, to produce hydrogen, especially through the photoelectrochemical water splitting process. The second example is to try to address the stability issue of the perovskite and for the solar cell and other device. And the third one is to try to combine the solar energy conversion plus storage and to have some integrated system. And with this, I would thank my colleagues. There are so many. I want to go through everyone. But finally, I also would like to thank my team, and they did all the work. I'm just talking. With this, thank you, everyone, and happy to answer any question.
Thank you very much, Lianzhou, for a great talk. Now, let me just start to introduce let me just introduce our panelists tonight so that we can really have a discussion of your exciting work. So our first panelist of tonight is Professor Huanping Zhou from Peking University. Professor Zhou received her PhD in inorganic chemistry from Peking University in 2010. And after that, she joined the University of California, Los Angeles as a postdoc researcher. And then from 2015, she joined Peking University. Now she's a full professor, and particular a Boya professor and vice dean of the School of Material Science and Engineering. Professor Zhou is a material scientist with expertise in the fields of nanoscience, thin film optoelectronic materials, and energy conversion devices such as solar cells, light emitting diodes, and etc. She has published more than 160 papers in very highly ranked journals such as Science, Nature, Energy, Nature, Communication, Geo, and JAX at Advanced Materials, and with citation over 28,000. And for 4 consecutive years, she was selected as highly cited researcher by Clarivate Analytics. Professor Zhou also receives lots of awards, including the first MIT Technology Review in China on 18th Global Technology Innovation 35 under 15 list, and etc. So I'm not going to list all of them. Professor Zhou also serves on editorial boards of several journals, and as well as she has also received, the 17th China Young Female Scientist Award. So that's our first panelist. Welcome. Our second panelist is Professor Yi Du, who is now theme leader of surface physics and quantum matter in the School of Physics at Beihang University. And also he's an honorary professor in the University of Wollongong in Australia. Professor Du's research interests include exploration and development of two-dimensional materials, liquid metal, functional materials for energy conversion by investigating the surface physical and chemical properties. Professor Du was awarded ARC Future Fellowship in Australia and also high-level talent recruitment project in China. He published more than 230 papers in international journals, including Science Advanced, Advanced Material, Nanoletter, etc., and with very citation over 9,000 and H index of 55. Professor Du also served as editorial board member of the journals Microstructures and Frontiers in Chemistry. Our ex-challenger tonight is Zhongyang Ren, who is now a PhD student at Peking University. Mr. Ren received his bachelor degree from Fuzhou University in 2017. He is currently doing his PhD at the National Key Laboratory of Nano Microfabrication Technology School of Integrated Circuits at Peking University. His research is on energy and nanoelectronics. Now let's welcome our panelists all to the stage to discuss about Lianzhou's exciting work. So of course, as usual, our first question will go to our ex-challenger, who is Zhongyang. Zhongyang, stage is yours.
Yeah, thank you. Thank you, Professor Wang, for your wonderful report. I have two questions. So first, I noticed that you approach using the perovskite and move improve device stability. Is this a universal approach? And does it apply to all perovskite materials?
Thank you, Zhongyang. I would say that the process is very simple, and so we the perovskite itself can have actually a very diverse composition. I think Professor Zhu know this. So the things we are doing is now just using the ball milling process to produce the composite, basically mix them together. And the key idea here is to choose the morph material, which can have the glass function. That means if you heat the material and at certain temperature, 200 and 250 something, if it's not damage the the perovskite material, but also can actually help the morph glass to form and to wrap. That means to coat the perovskite surface, and so I think that's the key idea. So in this case, and we needed to have the two material both have need to read to satisfy two criteria. The first one is the perovskite material, and certainly it shows stability at a certain temperature, and this can also be, if it's totally damaged at certain temperature, that's not good. And the second one is the morph glass, and which should have can become so like the morph can form some amorphous structure at a certain temperature. For this reason, it will form a very good surrounding layer to protect the perovskite. It should be universal, should be generic, but certainly we need to just look at the different composition, look at the different experiments, setting. So maybe some need a high temperature, some need a low temperature, but I think in a broad way, and this type of material should be generic.
Thank you, Professor Wang. The second question, the effective area of solar cell is very important for power generation. Also, however, the large effective area will affect the photoelectric conversion efficiency. So how to balance the relationship between the effective area and the photoelectric conversion efficiency.
So can I understand your question? You said that what's the meaning of the effective area?
Yeah.
The effective area in solar cell, you mean?
Yeah.
The size
the
of
solar cells as the area.
Solar cell area, and then what's the other one?
The photoelectric conversion efficiency.
Okay, so you mean if you want to prepare the solar cell at a very high size, but still try to keep the photo conversion efficiency.
Yeah.
Yes. Okay. So certainly this is a very challenging question, very tricky one, and if we for all our solar cell, I think Professor Zhou should maybe agree with us. So, and if we want to achieve very high efficiency, normally we will use a very small solar cell, and that's basically very like 0.0 something, 0.1 centimeter squared. So, but if you go larger, go to module size, so there are a lot of challenging engineering process actually need to optimize to try to keep the efficiency as high as possible. And so that's basically a lot of efforts if you increase the size. And so the active size from, you have from 1 square centimeter and go to 10, go to 100. I think another panelist, Professor Lianzhou, is also expert in this solar cell area. And it's very challenging. It's not only from, I think many of our colleagues in the solar cell area, they can do very good job, like Professor Liu Yanhan from Shanghai Jiao Tong University and others. And certainly there are some from Huazhong University of Technology. They're doing a lot of large scale module and still keep relatively high efficiency. So they're, but certainly if you really we want to go to the practical side, commercialized scale, there's still a lot of more work to do. And not only the scale, the size, the efficiency, but also the long-term stability is another important consideration.
Yeah. Okay, thank you. Thank you, Professor Wang.
Thank you very much. And maybe Professor Zhou have some further comments, I believe.
Great, thank you, Zhongyan. So, Professor Zhou, do you have any comments on that?
Hi, maybe I have some question.
Okay, yeah, please.
Thanks for Professor Wang's very nice talk. Actually, I learned a lot from this talk. So I guess all the audience knows Professor Wang done a lot of beautiful work on the photocatalyst and also the perovskite solar cells and other things. So one thing I like to ask for the perovskite materials. So you have done the quantum dots, the perovskite coated with MOF, and also other like you are doing the perovskite solar cells by using the carbon based materials as the transport materials. So for the commercialization, how do you think which direction is the most promising one?
This is a tricky question. This maybe $1 million question, I would say. Is certainly for solar cell, I think we have been working on this quantum dot solar cell for not quantum dots. I think the perovskite solar cell for quite some years, but we found that this area has been so competitive, and I think like your team, like and your colleagues, are also like Professor Jingbi, you recently published the paper last week, and so you can also can achieve very high efficiency and in the quantum dots and in the perovskite solar cell field, I mean the bulk field. So this area we found from our perspective, we found we may not be so competitive in this very crowded area. And so we choose to go for the other ones, go to the niche application. So like the quantum dots one, we want to try to go to the flexible and semi-transparent. So this is one approach, and we also are working with some companies and try to develop some, they have the lighting, for example, LED related one, QLED developed one. So in the bulk based one, we haven't done too much work, and so certainly because as I said, this area still have some challenge. But I think from a long term, still the high efficiency, stable perovskite at low cost is, I think, is still the most promising market. And if we cannot compete with the silicon-based one for the short term, at least we're talking about maybe 5 years, 10 years lifetime, for example. If we can, we're not talking about 10 years, but certainly if you can go with the tandem design, and so in combined with other silicon or other CGTS type, and this maybe it's also another important area, because that's will be sort of lifted by the other commercial products like silicon. But silicon based ones now, the market is huge, and so this is just my opinion, and I believe actually you maybe also have some good idea about how to go to the next stage. What's the most promising one, and maybe yours one is the most promising one, I would say.
I think the quantum dots, if you find the niche market, maybe a good one, since the stability is quite good. So
yes.
How is the stability of the quantum dots, the perovskite quantum dots? Is that material super stable, or it's not?
So we cannot say it's super stable, and if you look at the paper, certainly compared with the bulk film and the same condition, for example, the same composition, it shows some advantage. But if you look at the material prepared itself, because the quantum dot synthesis is very sensitive, and to the precursor, to the condition, and to the surface ligand, and sometimes because the colloidal processing and the surface ligand concentration control is really need expert. So, and that's the people who have been working on this maybe for years and who can develop some high efficiency one. The others may take 1 or 2 years to learn, get there, but still actually cannot. That's the tricky point. But if we can manage to prepare the quantum dots at high quality and with high reproducibility, certainly, and so the quantum dots should be able to show some advantage, like actually because multi-junction, the excitation, and the other advantage actually the bulk may not be able to achieve. So I think it's still the lighting maybe is the one direction in this regard with the QL and QLED. But as I said, the stability compared with other type of quantum dots, like the most stable ones and sulfur-based one, it's still needed further improvement for the perovskite-based one.
Thank you. We may just move to Professor Yi. Do you have any question to Lianzhou?
Yes. That is great talk, and it's always been enjoying to have talk with Professor Wang. So I just have 2 questions. The first one is, as you know, I'm doing a lot of work on the surface science. So in terms of the photoconversion materials, we know the surface structures and electronic structures is a key factors on the energy conversion efficiency. So in your opinion, how we can control, the surface states to achieve the higher efficiency? If there has any general method or the general idea or the strategy to to use surface structures to improve the efficiency in terms of the photo conversion materials.
So you mean the photo conversion? So basically, I'm talking about two. So you mean the photo catalytic process or photoelectric?
Yes.
Photoelectric chemical process.
Yeah.
So the surface, I think basically this is the interfacial, because interfacial engineering, and that's a lot of things, because so many charge transport actually through the interface. The interface, can be the in the bulk, and between solid to liquid, and in some ways in the photocatalytic area is solid to gas, solid between solid and gas. There's a lot of transport. So, and what we really want is to try to design the system that can on the surface. There will be some good, like for example, band bending, and to provide some driving force and for the charge trying to pass through quickly, and also try to minimize the defects. So on the surface, the defects normally is a lot of defects on the surface, on the interfacial range. That's what we really want. And so maybe Lan, you also have some comments, because this also related to yours one is 3.5 group semiconductor material. The heterojunction is the structure, the interfacial engineering certainly is the key. I think very important.
That's exactly, yes. Well, so all one of our research is always focused on how to design a good interface and also heterostructure to facilitate. So it's always the effort there, but yeah, yes. Keep going.
Yeah, that's great. Yeah, the second one is I just wanted to have your comments on. Do you have any perspective idea on what is the next generation solar cells? Like we have different systems, right? So we have very conventional silicon solar cell, and recently we have like the single crystal silicon, which has already reached to a very high the conversion rates, and also we have perovskite, but they has like a lot of drawbacks. So in terms of like the true system solar cells, can you just comment which one will be the future star, and what is like the simpler for the pathway for the development of the different type of the solar cells?
Maybe I'm biased. I think because we are working on perovskite, I think perovskite will be the future. So, but certainly there are a lot of challenge, and maybe some people working on OPV, they will have some different opinion. Like I think Professor Zhou maybe also some comments. The OPV also have a very high efficiency in recent years, and it's a push. And very, very quickly, this around 20% already, and it can also be very cheap. Maybe the stability can also be very good, and so I think it's good for the area in solar cell. If you have 2 or 3 technology, the competing, that means actually for each of the technology, they have their own sort of unique feature or the advantage, and so we may also borrow the idea from each other and try to actually to further improve the technology. So as a whole, so the ultimate goal certainly is to achieve high efficiency, stability, low cost, and also less toxicity. From this aspect, I think perovskite also have another the disadvantage is the toxicity.
Okay, thanks for that. Yeah, that is my questions. Yeah.
Thank you. I also have 2 questions from the audience, so I'll just read it out. So this first one is from Xin Liang from Nanjing. They said, "Thanks, Professor Wang, your wonderful talk. We follow your work for a long time. I want to ask you for the commercialization of train battery. What stage is that now, and how about the price? And what is the biggest challenge so far?"
Okay, thank you. And this printed battery is a collaboration between Brisbane, our local company, and the UQ's team. And so currently, so for the trial, and like a small size battery, is no problem. And the problem now is in the company side, and because they have the large scale production line. So in Arizona of US, that's in the desert and it's dry, and so no need to consider the humidity issue. So, but the problem now is they have a little bit issue to have the large scale production because you need from the small scale, like we had a trial last year on our campus, and there's no any problem. But if you want to do, for example, we currently, if we use the lab type of production, we can produce 100,000 a day. So for this type of battery, but for the company last year alone, they received 120,000 orders, but they couldn't do it. So they because of pandemic, the COVID, and they have something, actually some issues. They try to make the production line working as soon as possible. But so last month I saw the CEO for the company, and so they said actually by the end of the year they may be able to start to produce, and the target for them is to target on the very large events, sports event like marathon events, for example, tens of thousands of people, and to use this type of technology. Another companies, so actually they also working on the printed and battery, and with some like a healthcare device, and then basically they want to for monitor the health system. That's another thing they are doing, and in particular for this printed battery plus some RFID for the name tag, and I think it will be very soon this product, and because we already passed the first trial also last year.
Great, thank you. The second question is from Wei Zhang. He's asking, what are the commercial viable STH efficiency and cost? What are we now toward commercial application? And also, what are the challenges in scaling up production?
For which technology?
STH. Not STH.
Oh, solar to hydrogen.
Okay, yeah, that's it.
Sorry, yeah. This one I would say is still takes some time, and because the solar to hydrogen conversion efficiency in the system, in the photocatalytic system is still very low, and this is no doubt, and this maybe is another race between the hydrogen production by photocatalyst and PV driven EC process. And if you look at the technology and the photovoltaic plus catalysis or electrolysis to split water, and now have advantage already, and I think they nearly reached the point actually to be compatible with the gas reforming process. And if you look at the commercial side, there are a lot of demonstration already, and so like the electrolyzer plus the solar panel to drive this process, and which can produce hydrogen at a relatively low cost, but certainly haven't reached the point that's be similar price as the other ones, but it's already going down very quickly. That's mainly, I think, in my view, it's because of the PV price in the past 1 decade have dropped so much. And so if you go back to 10 years ago, the PV price and compare now, and it's only a few percent of the previous 10 years ago. that's actually driving all the costs down. And for the photocatalyst process, I would say we are running a bit late, and like a race, and we are much slower than the other side, and so still a long way to go, unless some of our people, like many maybe young talents in the audience, they can find some magic material and that can significantly improve the solar to hydrogen conversion efficiency. For example, by order of magnitude, and so like 10 times, and this will help. Otherwise, I think this process will be relatively challenging. But that doesn't mean the solar to chemical conversion, like the photocatalyst process, has no hope, because in the past 5 decades, and so many researchers working in this area, they already accumulate very rich knowledge, like the photochemical synthesis. And if we say you using the solar the photocatalytic or photoelectric catalytic process to produce hydrogen, you can generate hydrogen, with the cost of, for example, $3-4 per kilogram. This is not worth it. But if you produce some valuable chemical, and other than the hydrogen, which can have maybe 10 times more expensive than hydrogen, but using the same photo-induced reaction, because the photo-induced hole and electrons, they can do the redox reaction anyway. And if not split water, they can doing some more valuable chemical production. They can do the same thing. And so in this case, there's still plenty of room and for the photosynthesis, photochemical process to produce more valuable chemicals, I think. Like, for example, CO2 reduction to produce methanol, other things. They can follow exactly the same mechanism. And so there's still a lot of opportunity there, obviously.
Great, thank you very much, Lianzhou. I think in view of time, we might have to stop here. So let's thank you, Lianzhou, again for a wonderful talk, and also thanks for our panelists for a great discussion. And also thank you for everyone to watch tonight. So to finish, let me first representing ICANX to present this certificate or appreciation to Professor Lianzhou Wang for delivering a wonderful talk on semiconductor nanomaterials for solar energy conversion. And just a little advertisement for next week, we'll have our ICANX 112 on translational medicine underpinned by drug delivery malaria case study will be delivered by Professor Kelly Chibao from University of Cape Town. So please stay tuned for next Friday night. And from us now, good night, everyone. Thank you very much.
Thank you.
Okay.
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够相 奇迹。我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can，没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can， 没有什么可以阻挡心中无限的力量。I can。